Welcome to the RBFS Fundamentals Training Series. In this video, we're diving into the policy framework, one of the key components in RBFS. So what are policies? Policies control the flow of routing information in protocols like BGP, OSPF, or ISAS. They're also used to modify route parameters that are part of a routing update. The nice thing about the policy framework in RBFS is that it's generic. That means it's not tied to any specific routing protocol. A quick heads up before we begin, this video is free to use for non-commercial purposes and is designed to help you get familiar with RBFS through self-study. Keep in mind that it doesn't cover every possible configuration option available in RBFS, and implementations may change in future versions. Here's what we're going to cover in this clip. First, a high-level look at the policy framework. We'll break down the building blocks of a policy. Then, we'll move into the match logic with detailed examples to show how it works. We'll also introduce policy lists and policy chaining, powerful tools to help simplify large or complex configurations. Next, we'll touch on the concept of policy conditions. And finally, we'll walk through the actions that policies can perform and show you how to test them safely, without applying them in a live environment. This section introduces the routing policy framework in RBFS, outlines its main components, and explains how policies are constructed and implemented. The goal is to illustrate how routing policies are used to shape traffic behavior, enforce business logic, and maintain control over route exchange in large-scale networks. A routing policy is a structured set of rules used to control the selection, modification, acceptance, and advertisement of routing information within and between networks. It acts as a decision-making layer that aligns network behavior with business objectives. Routing policies influence which routes are accepted from or advertised to peers. They also define how routes are preferred or deprioritized based on attributes like IGP metric, AS path length, or local preference. Last but not least, traffic engineering decisions, such as load balancing or route selection based on cost, latency, or reliability are driven by policies. Routing policies are especially critical in service provider networks, where managing inter-AS traffic using BGP is essential. Policies help optimize traffic paths, enforce security by blocking invalid or malicious prefixes, enable redundancy, and reduce transit costs by preferring more economical paths. RBFS provides a modular and extensible policy framework that can be applied across multiple routing scenarios. Policies govern the import and export of routes between routing instances, ensuring VPN route segregation and correct redistribution. This is mainly used in BGP MPLS L3 VPN implementations. Policies determine which prefixes are accepted from or advertised to BGP neighbors. They can also manipulate attributes to influence upstream or downstream traffic engineering. When routes are redistributed between different protocols, for instance, from static routes into OSPF or BGP, policies define which routes qualify for redistribution and how they are transformed. Policies can filter multicast group memberships, improving control over group access and traffic propagation. The RBFS policy framework consists of four core components: the policy repository, the command processing module, the policy server, and the policy client. The policy repository is a centralized store containing all defined policies and their associated match action logic. It includes structured tables that define match conditions and corresponding actions. The command processing module is part of the configuration daemon. This module serves as the user interface layer. It translates CLI or API input into internal policy representations and stores them in the policy repository. The heart of the policy architecture is the policy server. It is responsible for parsing and validating policy objects. The policy server also resolves interdependencies between policy components. Afterwards, it translates high-level policy definitions into compiled C code for high-performance execution. Finally, it manages attachment points and notifies relevant daemons when policy changes occur. The policy client is a shared library embedded in client daemons such as BGP, ISAS, or OSPF. The client performs policy enforcement locally, invoking compiled policy logic to evaluate and act on routing information. Policies in RBFS are defined using policy statements, which are named entities that encapsulate routing decision logic. These statements are referenced by client protocols to apply routing policies during operations. Each policy statement consists of one or more ordered blocks known as ordinals. Every ordinal is assigned an execution order and contains two components, the match block and the action block. The match block specifies the conditions under which the ordinal applies. Multiple match rules can be configured, for instance, prefix filters, BGP attributes, and next hop IP addresses. These conditions can be combined using logical operations to form complex matching criteria. The action block defines the outcome when a match is found. At its simplest, the action may accept or reject a route. More advanced actions can modify route attributes, for example, setting the local preference, prepending the AS path, or changing the next hop IP address. Ordinals within a policy are evaluated sequentially. By default, the first matching ordinal determines the action taken. However, policies can be explicitly configured to continue evaluating subsequent ordinals after a match. Let's see how to configure routing policies. Usually, I demonstrate the configuration step by step on a real RBFS system first, and then summarize the commands for reference. However, since the policy components can be difficult to understand without knowing what to look for, let's approach it the other way around this time. We create a new policy using the set policy statement command, where we first define a policy name. Following the keyword ordinal is the ordinal number, an unsigned integer that defines the sequence in which the ordinals are executed. Note that RBFS does not support CLI features like insert before or insert after, nor does it provide a mechanism to renumber the ordinals. Therefore, it's a good idea to leave gaps between ordinal numbers to allow for future additions. After the ordinal, you configure either a match rule or an action rule. A match rule is assigned a rule number to make it unique. In the case of multiple match rules, their order does not matter. Each match rule consists of a type, which defines the attribute to match, a value type, which defines the format of the attribute value, a match type, which defines how the attribute is compared to the value, and the attribute value itself. Each ordinal must also have one or more action rules. These are also assigned integer rule numbers. However, unlike match rules, action rules are executed in the order of their rule numbers, meaning that a later rule can override an action applied earlier. Each action rule must have an operation assigned. This can be return permit to accept the route or return deny to reject it. There are also operations to modify route attributes. Depending on the defined operation, you may need to specify a type and a value. For instance, return permit simply accepts the route without any additional parameters, while adjusting the IGP metric requires setting the type to IGP metric and the value to the desired metric. A policy statement has no effect unless it is bound to a protocol or routing instance. There are three main groups of attachment points where routing policies can be applied in RBFS. All dynamic routing protocols allow importing routes from external sources using the redistribute command. The format of the command depends on the routing protocol. We've listed all variations here. Without any further options, all routes from the source protocol will be imported. For example, configuring redistribute direct will import all directly connected subnets. You can add the option policy name to apply a filter that defines which routes should be redistributed. While link state protocols such as OSPF or ISAS do not support route filtering between neighbors due to the link state philosophy that all nodes must share the same information, protocols such as BGP and LDP do allow control over the flow of route updates or label mappings in both directions. In BGP, routing policies are attached at the peer group level on a per-address family basis. In LDP, they are attached per LDP session. In RBFS, it is also possible to control the import and export of routes into routing instances using policies. The most common example is BGP MPLS L3 VPNs, where the routing instance represents a VRF. In this case, policies are applied at the BGP address family level, typically filtering based on route target extended community attributes to define the VPN topology. With this theoretical background, let's switch to the CLI of router R1, which is running RBFS version 25.2.1 in a virtual environment. The lab setup consists of 4 routers in total, all running eBGP between each other. The eBGP configuration is already in place. Router R4 is injecting several routes into the network, which we will use in the next section to demonstrate BGP import policies. In this first demo, we'll look at route redistribution. R1 has 3 interfaces with IPv4 addresses configured, the link to R2, the link to R3, and the loopback interface. Redistribution of directly connected routes into BGP is already configured, so R1 advertises the 3 corresponding prefixes to its neighbors R2 and R3. Now, let's create a policy that only redistributes the prefix associated with the loopback interface into BGP. We begin by creating a policy using the command set policy statement loop_only. This sets the name of our policy. Next we define ordinal 1 and create match rule 1 of type IPv4 prefix. The value type of the match rule is set to discrete, meaning that we define a single, atomic value. The match type is configured as exact, which means that the prefix must match the given value exactly. Finally, the value of the match rule is set to 192.168.0.1/32, which is the IPv4 address of the loopback interface. We don't want to modify any route attributes, so the only action rule in ordinal 1 specifies the operation as return permit, indicating that we want to accept the matching route. The default action for all unmatched prefixes is return deny, so there's no need to add a second ordinal. Next, we apply the policy to the appropriate attachment point using the following command: set instance default protocol BGP address family IPv4 unicast redistribute direct. We set the policy to loop_only and commit the configuration. Inspecting the prefixes advertised to R2, we can confirm that only the loopback address is exported from the local AS. Let's now shift our focus to match rules and take a closer look at how they work. We already know that match rules define the criteria used by the policy framework to evaluate routes. If a route meets the conditions in the match rule, then the action we've configured will be applied. Each match block can include 1 or more match rules. If there's just a single rule, it either matches or it doesn't, pretty straightforward. But if there are multiple match rules, the outcome depends on a parameter called the match logic. Now, the match logic can be set individually for each ordinal which represents a match block of the policy. If the logic is set to OR, which is the default, then just one of the match rules needs to match. But if it's set to AND, then all of them must match for the policy to consider it a hit. If a match block doesn't match at all, then the router simply skips the action part and moves on to the next ordinal in the policy. And here's a useful tip. If you define an ordinal with an action block but leave the match block empty, then it will match every route, basically acting like a match all condition. Earlier, we saw that each match rule has 4 parts you need to configure. Let's go over them quickly. First, there's the type. This tells the router what kind of attribute you want to check. You might match based on things like IPv4 prefix, IPv6 prefix, IPv4 next hop, or even BGP attributes like AS path, community, or local preference. Second, you choose the match type. This defines how the match is done. For example, exact means the route must match the value exactly. Regex lets you use Linux-style regular expressions, which is especially useful when working with communities. For numeric attributes like IGP metrics or local preference, you can use match types like greater, greater or exact, less or exact. And when working with prefixes, there are special match types just for prefix lengths. Third, there's the value type. This is usually either discrete, meaning a single value, or list, which lets you match against multiple values. And finally, you need to define the actual value. What that looks like depends on the type you picked. For example, if you're matching an IGP metric, the value will be an unsigned integer. But if you're matching a next hop, then it'll be an IPv4 or IPv6 address. Matching IPv4 and IPv6 prefixes is an important task in routing policies, so let's go a bit deeper into the match types used for this purpose. To illustrate, let's take the IPv4 prefix 192.168.0.0/24. We've already used the match type exact in our earlier example. As the name suggests, it results in a match only if the prefix being evaluated matches exactly, same network and same prefix length. But in practice, we often need to work with subnets of a given prefix. Matching each one individually would take a lot of effort if it's even possible. That's where the match type longer comes in. This match type includes all real subnets of the given prefix. For example, any network that shares the first 24 bits and has a longer prefix length, like /25, /26, and so on would be matched by longer, for instance, 192.168.0.64/27. Now, if you want to match both the prefix itself and all of its subnets, you can use the combined match type or longer. This includes an exact match and anything longer than that. Let's take a moment to configure a prefix filter to demonstrate how this works. When inspecting the prefixes advertised by router R3, we notice a couple of them. In our lab environment, we use prefixes from the 172.16.0.0/12 network for link addresses and customer networks, and prefixes from the 192.168.0.0/16 network for loopback addresses. However, we do not use any networks from the 10.0.0.0/8 block. So let's block them by writing a policy named net10. We do this using the command set policy statement net10 ordinal 1 match rule 1. We set the type to IPv4 prefix, as before. The value type is discrete, and the match type is set to or longer instead of exact, since we don't want to write individual rules for each subnet, just a single catch-all rule. The value is set to 10.0.0.0/8. For the corresponding action rule, we set the operation to return deny, as we want to reject this prefix and all its subnets. Next, we attach the policy to R3 using the command set instance default protocol BGP peer group ISP3 address family IPv4 unicast policy import net10. After committing the configuration, we can confirm that these prefixes are now blocked. The show route command output shows only R2 as the next hop for these routes. However, we also notice that no BGP prefixes are being accepted from R3. R3 does not appear as a next hop in the routing table at all. The reason for this is that our policy does not include an ordinal to accept all unmatched prefixes, and by default, a policy rejects everything else at the end. We can fix this easily by adding a second ordinal with the action return permit. You might want to try this yourself. For now, we'll leave the policy as is and revisit it with another approach later. When working with large routing tables, just filtering by prefix might not be enough, especially if you're trying to control the size of the table. For example, you might want to block very small subnets, like /28 or /29. You could technically do this with or longer, but it would require a rule for every possible network whose small subnets you want to block. That's not very efficient. A better approach is to use prefix length matching. With prefix length matching, the prefix itself doesn't matter, only the length is evaluated. So, for example, 0.0.0.0/24 and 10.1.0.0/24 would have the same effect, because only the /24 part is used in the match. There are several match types for this. Prefix length exact matches all routes that have the exact same prefix length, like /24. Prefix length greater matches all prefixes that are more specific, like /25, /26, and so on. And finally, prefix length greater or exact combines the two, it matches both the specified prefix length and anything longer. To illustrate prefix length matching, let's consider the prefix 172.16.43.0/24. From the show route command output, we can see that in addition to the base prefix, we also have a number of subnets. Let's assume we want to filter out the /27, /28, and smaller subnets. We define a new policy using the command set policy statement import _ISP2 ordinal 1 match rule 1. The type is again IPv4 prefix. The value type is discrete, and the match type is now prefix length greater or exact. The value is set to 27, which is encoded as 0.0.0.0/27 where only the /27 matters. We can use another network. Since we also have a loopback prefix with a /32 that we want to keep, we add a second match rule to the same ordinal. This rule is also of type IPv4 prefix, but it is restricted to all subnets of the prefix 172.16.43.0/24. The action rule for this ordinal is return deny. As we saw in the previous example, the default action at the end of the policy is also return deny. So, to accept all unmatched prefixes, we add an additional ordinal, this time with a high number like 99, and set its action to return permit. We attach the policy using the command set instance default protocol BGP peer group ISP2 address family IPv4 unicast policy import _ISP2. After committing the configuration, we notice that not only the /27 and /28 prefixes are being blocked, but also the base prefix 172.16.43.0/24 and also the loopback prefixes. The issue here is that, by default, multiple match rules within a match block are combined using a logical OR. We need to change this behavior by setting the match logic to, and, using the command set policy statement import _ISP2 ordinal 1 match logic and. Once we do this, we can confirm that everything works as expected. Policy lists are used to match specific attributes of routes and then apply actions based on those matches by referencing them within a policy statement. Policy lists are configured separately and can be reused in multiple policies. This helps avoid duplicating configuration across different policy statements and reduces errors, as you have fewer touch points when updating entries. In addition, policy lists simplify configuration. Instead of creating a separate match rule for each value, you only need one match rule for the entire list. Entries within a policy list are logically connected via an OR relationship, meaning that the match rule is considered a match if at least one entry in the list matches. The most common type of policy list is a prefix list, which contains a set of IPv4 or IPv6 prefixes. However, policy lists can also include BGP communities or BGP-AS numbers. In RBFS, a policy list is created using the set policy list listname command. You need to define the type of policy list, for instance, IPv4 prefix. Each value you add to the list is assigned a unique ordinal. Since the entries in the list are evaluated as a logical OR, the order of the ordinals does not matter. The policy list is referenced within a policy statement by setting the match rule's value to the policy list name. Additionally, the value type must be changed to list instead of discrete. Note that the type of the policy list and the match rule must be the same. For illustration, we have provided a commonly used example, filtering RFC 1918 IPv4 addresses. A corresponding policy list is shown. With the policy list, you only need one match rule, as opposed to 3 separate rules in the policy statement. Moreover, the policy list can be modified without needing to adjust the policy statement. In the output of the show route command above, we can see 2 prefixes, 172.16.50.0/24 and 172.16.53.0/24, both of which we want to reject. To accomplish this, let's implement the policy list concept. First, we'll define a new policy list using the command set policy list prefix underscore list. Here prefix underscore list is the name of our list. We will configure the list to be of type IPv4 prefix and add two ordinals, one for each prefix we want to match. Next, we'll modify the existing policy statement import underscore ISP2 by adding a new rule. Specifically, we add ordinal 2 to the policy statement. The match rule for this new ordinal is set to the same type as the policy list. The value type is defined as list, and the match type is set to exact, ensuring that only the specified prefixes are filtered. The value is then set to the policy list name which we just created. Finally, we configure the action for the policy list to permit deny. After committing these changes, we can verify the outcome by running the show route command again. The two prefixes should no longer appear in the routing table. When implementing policies in BGP, the configuration can become quite long and complex, making it harder to read and more prone to errors. This complexity arises from the difficulty of tracking changes over time. In BGP, each external BGP peer typically requires an individual policy applied in both directions. However, certain parts of these policies are shared across multiple peers, for example, blocking RFC 1918 addresses, filtering private AS numbers, and so on. Policy chaining allows you to break down a complex, monolithic policy into smaller, more manageable policies, which are executed sequentially. This enables the reuse of certain policies across different chains, improving maintenance and simplifying updates by reducing the number of touchpoints. Policy chains also help to separate generic rules from peer-specific rules, keeping the configuration clean and minimizing complexity. Additionally, policy chaining reduces the amount of configuration code and improves readability, which simplifies troubleshooting. Configuring policy chains in RBFS is straightforward. You simply add multiple policies to the appropriate attachment point in the correct order of execution. When viewing the configuration in JSON format, you'll notice that the policies are stored as an ordered list. However, it's important to note that you cannot directly add a list via the CLI. As shown in the previous slide, a policy chain is executed as though all the policies within the chain are a single, large policy. Therefore, it's important to avoid using return permit or return deny for unmatched objects at the end of any individual policy, as doing so would prevent the execution from continuing to the next policy in the chain. In a previous example, we created a policy that rejected all prefixes from the 10.0.0.0/8 network and applied it as an import policy on router R3. However, because the policy did not include a return permit statement at the end, not only were the 10.0.0.0/8 prefixes rejected, but all other prefixes were also blocked. Upon reviewing the routes received from R2, we discovered that 3 prefixes from the 10.0.0.0/8 network are still present, which contradicts our business policy. To resolve both issues, we'll use policy chaining. Let's start with R3. We begin by creating a new policy named import underscore ISP3. This policy will have a single ordinal for now that accepts all routes. We assign ordinal 99 to ensure we can add more rules later if needed. Next, we apply this policy to the BGP peer group ISP3 as an import policy. When inspecting the new configuration in JSON format, we can confirm that the original policy net10 was not overwritten, but rather the new policy was appended, thus forming a policy chain. Inspecting the routing table confirms the result. The prefixes from the 10.0.0.0/8 network are rejected by the net10 policy, while the remaining prefixes are accepted by the import underscore ISP3 policy. Now, we want to apply the net10 policy also to router R2. Simply adding it at the end of the chain will not work, as the last policy in the chain, which is import_ISP2, already permits all unmatched prefixes. To resolve this, we need to insert the net10 policy at the beginning of the chain. Thus, we delete the old policy, then re-add the net10 and import_ISP2 policies in the correct order. In addition to the match rules we've covered so far, RBFS also supports an extra layer of control: policy conditions. A policy condition is a rule that's defined independently of the policy itself. It's an additional requirement that must be met before a policy ordinal can be executed. Unlike standard match blocks, which focus on parameters or metadata attached to the object being evaluated, policy conditions can also track the state of the system. In RBFS, this system state is represented by entries in BDS tables. To configure a policy condition, you'll need to specify which BDS table should be consulted, and which brick daemon is responsible for evaluating the condition. There are two ways to define a policy condition. You can match on the presence or value of an attribute in the BDS table. For example, you can check the state of a routing protocol neighbor or look for the presence of a specific route. Alternatively, you can match on the number of entries in a BDS table, such as counting the number of IPv4 routes. To set up a policy condition, use the setPolicyCondition command. You'll define the BDS table and specify the daemon that will evaluate the condition. Depending on the type of condition, you'll either match an attribute and value or set a count with a match type. Finally, assign the policy condition to a policy statement at the ordinal level. Each ordinal can only have one condition, but a single condition can be used in multiple policies. Let's briefly examine how policy conditions operate in practice. We begin by inspecting the IPv4 unicast routing table in the Brick data store using the showDataStore command. First, we need to specify the brick daemon, in this case, ribd, and then provide the BDS table name default.ribd.fiblocal.ipv4.unicast. The output contains extensive information, but we're primarily interested in identifying the correct attribute name to define our policy condition. Since we want to match a specific IPv4 prefix, the relevant attribute name is prefix 4. Next, we define a policy condition using the setPolicyCondition command. We'll name this condition simple_condition. We specify the table name and the brick daemon, then configure the attribute, prefix 4 in our case, along with the match type and match value. In this example, we want to match the prefix 172.16.10.0/24 exactly. Previously, we defined a policy named loop_only that permits only the loopback address to be redistributed into BGP. We now modify this policy so that the loopback address is redistributed only if the prefix 172.16.10.0/24 is present in the IPv4 unicast routing table. To achieve this, we apply the policy condition to the policy using the command setPolicy statement loop_only ordinal 1 condition simple_condition. After activating the configuration, we verify the prefixes advertised by R1 to R3 that originate within the local AS. The output is empty. Upon checking the IPv4 routing table, we find that the prefix 172.16.10.0/24 is not present, confirming that the policy condition is functioning as expected. To test further, we create a static route for 172.16.10.0/24 and observe how this affects policy evaluation. Once the test prefix is present in the routing table, the loopback address is successfully advertised to R3. Now that we've covered match rules in detail, let's briefly discuss action rules. Just like the match block, each ordinal has an action block. This block contains one or more action rules that will only be executed if there's a match in the corresponding match block. Each action rule is defined by an operation that specifies what should be done. These operations fall into three categories. First, terminating action operations. As the name suggests, these operations end the evaluation of a route or object. They either accept the object with a return permit instruction or reject it using return deny. Second, flow control operations. Sometimes, after matching an object, we might want to delay the decision to accept or reject. In this case, flow control operations like goToNextOrdinal or goToNextPolicy are used to continue the evaluation process. Third, attribute modification operations. These operations change the values of attributes. You can overwrite an existing attribute with a new value, or modify it using numeric operations like add, subtract, multiply, or divide. For list-type attributes, like communities or AS paths, you can append or prepend values to the list. You can also delete values, either entirely or by removing certain items from the list. Like match rules, action rules are assigned rule numbers and executed in sequence. This is where order matters. Unlike match rules, the sequence of action rules is important because a terminating action might stop the process before any modifications are made. It can also happen that attribute values are changed multiple times, which could lead to inconsistencies. In our previous examples, we already made use of terminating actions, because at the end of the day, this is what policies are primarily about, accepting or rejecting routes. In this example, however, we aim to demonstrate how to modify prefix attributes. Upon inspecting the IPv4 routing table, we observe that all prefixes have been learned via R2 and R3, and most of them are equally viable through either path. Our goal now is to prefer prefixes advertised by R2 over those from R3. In BGP, the first attribute considered during route selection is the local preference. Therefore, we'll add a new ordinal to the policy import_ISP2 to adjust this attribute. We first define a match block using the set policy statement import_ISP2 ordinal 3 match rule 1 command that covers all prefixes within the 172.16.0.0/16 network. Next, we add an action rule of type local preference. We set the operation to overwrite, and assign the value 200. Because we want to avoid using a terminating action this time, we set action rule 2 to operation goToNextOrdinal instead. After committing the changes, we can confirm that most prefixes now have only R2 as next hop, indicating that the local preference adjustment has taken effect as intended. We already know that policies are only used if they're attached to a routing protocol or a routing instance. That's straightforward. However, the result of evaluating a complex policy can sometimes be hard to predict. Plus, lab environments might not always model real-world networks accurately. To safely test a policy without impacting the production network, RBFS provides a method to simulate policy execution against a BDS table using the test policy command. The test policy run command simulates policy execution. Along with the policy name you want to test, you need to specify the daemon that will evaluate the policy and the BDS table the policy will be tested against. The results of the test are stored in 2 new tables on the system. These table names match the original BDS table name, with a policy.permit and policy.deny prefix. If you no longer need the results, you can delete them using the test policy clear command. Here's a simple example. We've defined a policy that matches only on IPv4 host routes, those with a /32 prefix length. We then evaluate this policy using the Rtbrick daemon against the standard IPv4 routing table, which is stored in the BDS table default.rtbrick.fiblocal.ipv4.unicast. To run the test, you use the test policy run command with the appropriate parameters. The results will appear in the two newly created tables. To wrap up this video on the RBFS policy framework, let's go over some final remarks. The policy framework is a powerful and flexible tool that helps you implement routing policies. Features like prefix lists, policy chaining, and conditions can simplify many tasks. However, when configuring policy statements, most errors come from not being familiar with the default settings. So, let's summarize them. If an ordinal doesn't have a match block, all objects will be matched, and the action block will be executed. If a match block contains multiple match rules, they're combined with a logical OR, and the rule order doesn't matter. In an action block, the rule order does matter. Rules are executed in sequence, so make sure you don't terminate an action before all modifications are made. If you define an action block without a terminating action, the default action will be return permit. Finally, any unmatched objects will be rejected at the end of a policy or, in a policy chain, at the end of the last policy. As a best practice, it's a good idea to explicitly define action rule operations, even if they have default values. This improves readability, especially in multi-vendor environments where different implementations might have different defaults. I hope you enjoyed this clip on configuring routing policies in RBFS. If you like to study more examples, I recommend to watch the second part of the BGP video, where I present some BGP-related use cases. Thanks for your attention and see you soon for another video.